Good evening, viewer. Welcome to our Glory Globe TV. Here's breaking news. Yes, new experiments using one-dimensional gases of ultra-cold atoms reveal a universality in how quantum system composed of many particles change over time following a large influx of energy that throws the system out of equilibrium. A team of physicists at Penn State showed that these gases immediately respond, evolving with features that are common to all many body quantum systems thrown out of equilibrium in this way. A paper describing the experiments was published on May 17, 2023 in the journal Nature. Many major advances in physics over the last century have concerned the behavior of quantum systems with many particles, said David West, distinguished professor of physics at Penn State and one of the leaders of the research team. Despite the staggering array of diverse many-body phenomena like superconductivity, superfluidity, and magnetism, it was found that their behavior near equilibrium is often similar enough that they can be sorted into a small set of universal classes. In contrast, the behavior of systems that are far from equilibrium has yielded to few such unifying description. These quantum many-body systems are ensembles of particles like atoms that are free to move around relative to each other. West explained when there are some combination of dense and cold enough which can vary depending on the context. Quantum mechanics, the fundamental theory that describes the properties of nature at the atomic or subatomic scale, is required to describe their dynamics. Dramatically out of equilibrium systems are routinely created in particle accelerators when pairs of heavy ions collide at speeds at near the speed of light. The collision produces a plasma composed of the subatomic particles quarks and gluons that emerges very early in the collision and can be described by a hydrodynamic theory similar to the classical theory used to describe airflow or other moving fluids well before the plasma reaches local thermal equilibrium. But what happens in the astonishingly short time before hydrodynamic theory can be used? The physical process that occurs before hydrodynamics can be used has been called hydrodynamization, said Macros Rizal, professor of physics at Penn State and another leaders of the research team. Many theories have been developed to try to understand hydrodynamization in this collision, but the situation is quite complicated and it is not possible to actually observe it as it happens in the particle accelerator experiment. Using cold atom, we can observe what is happening during hydrodynamization. The Penn State researchers took advantage of two special features of one-dimensional gases which are trapped and cooled to near absolute zero by lasers in order to understand the evolution of the systems after it is thrown out of equilibrium. But before hydrodynamics can be applied, the first feature is experimental. Interactions in the experiment can be suddenly turned off at any point following the influx of energy, so the evolution of the system can be directly observed and measured. Specifically, they observed the time evolution of one-dimensional momentum distribution after the sudden quench in energy. Behind this report, Glory Globe TV, Delhi, India.